One of the things we do, of course, to review is we literally go page by page through the book. So, some of you weren't here on Friday. You missed that particular review for Monday's test. So I'll go through this again. Have your book with you. I'm trying to get my hands on a digital copy of your textbook, so this will make it a little easier. And when I do, the video will be perhaps a little bit more easy to follow. But have your textbook as we go through so that you can remember or remind yourself what will be on the test, what won't, skills that you need to practice and demonstrate, and skills that you won't. So this particular chapter really pulls itself together on page 80. Oh, I'm not writing all this in pink ink. That's not going to happen. Okay, let's go to blue here. Make that a little bit more eye-friendly. Page 80, this chapter starts with a section called Introduction to Vectors. So make sure in terms of definitions, you have vector and scalar. Know what those mean and examples of each. So a vector is a quantity that has a magnitude, a how much, and a direction, where to. Scalars only possess a magnitude. They don't have a direction. It's not appropriate for the type of quantity. So things that are vectors. We've talked about in kinematics, velocity, displacement, acceleration. Other examples are things such as force and momentum, who, yes, his variable is a little p. Scalars, speed, distance, but also things such as just simply number of dogs, scalar, mass, and temperature. So make sure you're very clear on the definitions of each, and you can come up or recognize some examples of each. Now when we deal with the idea of vectors, page 81, know the term resultant. That when we're dealing with vectors, if I sum two together, add them together, the answer is the resultant. Whether it is two that are perpendicular to each other, and there's the resultant, whether they're not perpendicular to each other, that's the resultant. And it can be the sum of 50 vectors. It doesn't really matter. Here, 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 here. What's the resultant? Where did I start? And where did I end? And all resultants, because it is a vector, must have a magnitude, and a direction. Now to find that magnitude and direction, there are two ways we could do it. So still on page 81, we have what's called the graphical method. You, as I said in class, will not have to demonstrate this on a test, but you should know it exists. That if I have two vectors, or 3 or 4 or 5, it doesn't matter. I can actually draw them to scale using a ruler and assess angle using a protractor. So if I have two vectors, I can measure out exactly to scale the length of one, exactly to scale the length of the other, lay my ruler down, measure the resultant to get the magnitude with the ruler, use a protractor to get the angle. It works, it definitely works, but it's time consuming, it's prone to some error if you're not careful, and of course it needs some special materials. So graphical method is not one that, as I said, we tend to use very often, but do know what it is and how I would use it in order to get an answer. Now whether it's the the graphical method or not, if we look on page 82, you see information about properties of vectors. Very importantly, vectors can be moved parallel to themselves. So if I have this vector and I have, this vector. Draw him in. Poof, poof, poof. Okay. I have those two vectors. I can take either one of these. For example, let's take the diagonal one. There's no reason I can't draw him like this. In other words, pick him up and move him parallel to himself. I didn't change the direction. The arrows are still pointing the same way. And I didn't change the length. I didn't change the magnitude. That is perfectly allowed. So if I take a look at what my resultant would look like for the two blue vectors, my resultant would look a little something like this. Doop, 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 doop. How about for the blue and the pink? Beep, 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 beep. Same magnitude and same direction. In other words, I get the same answer regardless. And that really brings us to the second thing about vectors. You can add them in any order. So if I have 10 vectors, I'm not going to draw 10, but let's say I have this one, this one, this one, and that one. I can easily reorder them. I can have that guy first, that guy second, this little guy third, and that guy fourth. You know what? Beep, 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 beep. I'm going to get the same answer. So when making diagrams that contain more than one vector, you can move them around. The two things you can't do. One, can't change direction. That is not allowed. Two, can't change magnitude. But you are welcome to, as I said, change needs need, reconfigure your diagram to make it a little bit easier to work with. The other thing that's absolutely critical is 3. Always add tip to tail. That is paramount in importance when we're working with our vectors. So if I have a few vectors, let's say I just have this guy, I'm going to add him to this guy, and then I'm going to add him to that guy. I have to add such that the tip of one will always touch the tail of another. I can never go tip to tip. Bloop. I can never go tail to tail. So for these 3, I could go him first, add to him, and then add that guy. That's fine. I could add him first, then him, then him. That's fine. But what I cannot do is add this guy and that guy and that guy. I can't add them all tail to tail or tip to tip. So make sure if you have multiple vectors, however many there are, in any order, it doesn't matter. As long as you're always adding tip to tail, tip to tail, tip to tail, tip to tail, you're going to be fine. Now between page 82 and 83, I said don't worry about subtracting vectors or multiplying vectors. That's not really on our plates at this moment in time. Starting on page 84, I'm in green ink now. Okay, green ink is fine. As with all sections, it does pay just to take a look at the objectives, and it does pay to look at any key terms. But remember, of course, that our key terms, there are often other very important vocabulary items embedded. They're often in italics or something like that, but it's a good place to kind of start to orient yourself. This section called Vector Operations brings up that all vectors, every single one, have 2 components. All vectors have an x and a y. Every single one can be defined by an x and a y coordinate. So we see on page 84 the chameleon, or the lizard, who's actually climbing the tree. His vector is all in the y. So for his x, it's 0, and the y has some value. That's fine. It's still 2 coordinates. Your airplane had a defined x and a defined y. That's okay. So if I had drawn another one like this, he'd have some x value and 0 is his y. And that, of course, became very important as we started to work with vectors. that when I go to put them together or work with them, working with the x and working with the y are two very important things to be able to do separately. On page 85, we start to now work with vectors, not with the graphical method, but using some mathematical techniques. If I want to sum vectors, in other words, add them together, we started with a situation where we had vectors that were perpendicular to each other. They make right angles. There, emphasize it. When I have perpendicular vectors, I have one that's going to be x direction only, one that's going to be y direction only. And in order to look at something like that, something like this versus like this, and find a resultant, I had two things to do. To get the magnitude of the resultant, use the Pythagorean theorem. A squared plus b squared is c squared. So c is the square root of a squared plus b squared. That would give you the magnitude. And don't forget, it also has a unit. Don't forget your unit. So if this is a displacement vector and that's a displacement vector, make sure your resultant's unit reflects as a displacement vector. But now what if I need now, of course, to get the angle? Because a vector must have an angle. That's actually the shoddiest perpendicular vectors I've ever seen. Here we go. So I solved for the magnitude using the Pythagorean theorem. I need a direction. Well, I had the x and I have the y sides. I did also add the hypotenuse if I wanted to use it. But at this point in time, when we turn over and look on page 86, they introduce the tangent function. The tangent of an angle is a ratio of two sides to the triangle. The side that's opposite the angle divided by the side that's the adjacent. So our angle right here that we see in this diagram, the side that's opposite the angle is your y side of the triangle. The side that's adjacent is the x. Now, solving for that ratio would give me the tangent of the angle. And really, that's not exactly what I want. I want the angle by himself. So the best way to go right into your calculator and solve for your angle is if you look at your calculator, you see that the tangent key has right above it another key that's tangent to the -1. You usually have to use something like a second function or something on your calculator to access it. But if you do tangent -1, in this case, y divided by x, you actually get the angle himself. Now, is it always y divided by x? No. I could have a triangle instead that looked like this. Oh, boom, ba-boom, and boom, ba-boom. And I'm looking for that angle. In that case, tan -1, x and y. This time, x is the opposite side, and y is the adjacent. So you do have to look at your diagram. Which angle are you looking at in terms of working the problem? How do the sides line up in terms of x of y? But that tan -1 key will give you the angle directly that you need. Now, the other thing we said with direction to be very clear about was when you have things such as north of east, west of south, south of east, etc. An angle, always, if they're giving you an angle, let's say, make sure you're very clear about defining your angle and answering the question really in detail. What is the direction that angle is trying to assess? So if I have something like this, the first example of the perpendicular vectors, if I know that this is an east vector and that is a north, my angle would be north of east, or northeast. So many degrees, 20, 30, 40, north of east. If I had this example, though, where I had this side and that side, and I want that angle, he is west of north, not northwest. We kind of in our brains get very hung up on northeast and northwest, southeast and southwest. But west of north, west of south, okay, east of south, or east of north are valid ways to talk about angles. Use the of and of sides of the triangle to give you a place to start. So if I had said I have an angle that's so many degrees west of south, mentally take your coordinate plane, I guess I can draw it as a solid line, of south, starting with the south axis. My angle is going west of that. So my angle is going to be somewhere right in there. I have south, I went to the west. It's that angle. Versus instead something that was south of west. Now my of axis is the west. The angle is going south of that. It's that guy right there. So in describing angles, I added this vector and that vector. My angle I probably report as south of west. Adding this vector and this vector, and I want that as my hypotenuse, I might report my answer instead. There's north, there's west, west of north. So go ahead and make sure that when you're reporting angles and working with angles that you are kind of lining them up and explaining them very, very well. Now sometimes I said when you're working with these, especially if you're solving for an angle, let's say you have this guy right there, and he's 20 degrees north of east. If when you worked the problem, you solved for that angle right there, that's okay. There's nothing wrong with that. It's not necessarily incorrect. But be very clear, when you tell me your angle is 70 degrees, you're telling me it's 70 degrees east of north. Because if you tell me it's 70 degrees north of east, I'm thinking he looks like this, that guy. And that's not right. So be very clear when you're doing work on problems. Sometimes you might solve for the wrong angle. Look at what your angle is saying, okay? And if there's a multiple choice question that looks like this, well, they're the same answer. You can use, that's either one of them is right. On an open response, this north of east or east of north part helps me to understand if you actually are looking at the right angle in terms of describing your resultant. So take the time and take the care to really pay attention to that. Now, combining two vectors that are perpendicular, what happens instead on page 88 if I have one vector and I need the two pieces to him? I need the x piece and I need the y piece. On page 88, we get into what is called resolving vectors. R-E-S-O-L-V-I-N-G. Resolving vectors is taking a resultant and breaking it into its x and y, even if one of the x, even if the x or the y happens to be 0. How do I do that? Well, your vector will be reported with some magnitude and the angle. And with that, you can go ahead and figure out exactly what those two sides would be using two more trig functions. The cosine function and the sine function. Cosine is a relationship between the adjacent side of a triangle to the angle in question and the hypotenuse. Sine is a relationship between the opposite side of the angle to the hypotenuse. So given the example over here on the left, if I want to find the size of that side, He is the side of the triangle adjacent to the angle. So I would use the cosine function. I know the value of my angle. I put him in there. I know the value of the hypotenuse. I put it in there. Cross multiplying would give me the value for the adjacent side. So sometimes you see me shortcut it. In fact, you often do, where it's hypotenuse times cosine of angle. So let's say our magnitude is actually 15 meters, and my angle is actually 40 degrees. To find the value for the x side of the triangle, 15 meters times cosine of 40 degrees. Because I would have here cosine of 40 equals adjacent divided by 15 meters, and I cross multiplied. To find the y side of that triangle, he is the side opposite the angle. So, same thing. I put in my angle right here, in this case 40, value for the hypotenuse, which is 15 meters, cross multiply would give me the value of that side. So he'd be 15 meters sine of 40. Now, some people do get very caught up on the fact that sine is for the y direction only and cosine is for the x. That's not necessarily the case. If I have two vectors that look like this, excuse me, we're resolving vectors. Boop, boop, boop. I have a vector that looks like this. He's so many meters, let's say 200 meters, and his angle is this guy, 20 degrees west of north. Well, to solve for my x side of my triangle, he is now suddenly the opposite side of the angle. My x side, or horizontal side of the triangle, 200 meters sine 20 degrees. And that also brings up an important point. That particular vector is pointing west. Remember, west, south, left, down are all considered negative directions. He would appropriately be given a negative value. My y direction is actually positive. So the y would be a positive. Adjacent side to the angle, I'd use the cosine function, 200 cosine of 20 degrees. And working then with my calculator, I would go ahead and I would get my information, and I would know the value reporting this guy, negative 200 meters sine 20, or if I want to say 200 meters sine 20 to the west, fine, positive 200 cosine 20, or 200 cosine 20 north, and get my answer and roll from there. So resolving vectors, taking one, breaking him to x and y, vector combination or vector addition, taking two separate vectors, adding them together to get a resultant. The question became, though, what happened if instead you had vectors that looked like this? One's like that, and the other's like that. And I need the resultant. Well, that's where we pick up on page 90 with non-perpendicular vectors. To work with non-perpendicular vectors, you had a series of steps. Number one, resolve each vector into his x and y pieces. So for each vector I had in my drawing, I would go ahead and take a look at his individual x and y pieces. His x looks like that. His y looks like that. His x and his y. And I would find those values, x1 and x2, y1 and y2. When I have those individual values, I'm going to sum the x and sum the y. So how much in total x am I covering? That much plus that much. How much in the y? That much positive, but that much negative. Pay close attention to signs. In this case, my positive x and positive x add together. But in this case, I have a positive y and a negative y, and they're going to be obviously subtracted from each other. Once I have that sum of the x and sum of the y as individual values, make a triangle. Your triangle will be sum of the x and sum of the y as your two sides. And I drew them both positive. They absolutely don't need to be both positive. It would depend upon what your answers were. If we found out that our y was actually a negative value, yes, I'd have sum of the x positive and sum of the y negative. Whatever your actual values are for here and here, use those to make the appropriate right triangle. And then once you've done that, get your resultant. Please do not forget you need magnitude and direction. And with that direction, go ahead and be as specific as possible. So I have a couple of videos that have been put up a few days ago, and I also have one today, dealing with working with non-perpendicular vectors. Go back and look at that if you need some help. Then we suddenly jump out of vectors, it seems completely, though we really don't, when we hit page 93, projectile motion. With projectile motion, make sure you know the definition of what a projectile is and examples. Projectile, object launched through the air, acted on only by gravity. Examples, throw a ball through the air, throw a rock through the air. Not a rocket that's moving with its engines lit, not an insect flapping its wings. Those are not parts of, or not examples of projectiles. When we're working with the idea of projectile motion, we're going to see motion in the x direction coupled with motion in the y direction. So for something like a ball rolling off a table, as the ball goes off the table, boop, he continues to move away from the table, like this. But at the same time, he's also falling down. And it's a combination of that motion that gives me the ultimate trajectory of a projectile, which is a parabola, which they bring up on page 94. All projectiles, whether I kick a ball and it lands on the ground, whether something leaves a table and lands bloop, onto the ground, the path is going to be parabolic. And it comes about because of the combination of the motion in the x and the motion in the y occurring simultaneously. Now on page 95, we jump over to that. Figure 3.4 is a nice little sort of summary of what's going on in projectile motion. When you have projectile motion, the x and the y components are independent. So you see the one ball that's been dropped straight down. And actually, I'll attempt to draw it a little bit more representational. And then you see the ball that's been launched a little horizontally. Let's see, I need him like about right here. By now, I hope everyone has recognized that Miss Cawthron is not at all an artist. So you have the two balls. You have the ball that's red and you have the ball that's yellow. Vertically, in the vertical direction, each ball falls at exactly the same rate. Each ball will hit the ground at the same time. At any point in time, each of those two balls has the same velocity in the y direction. The difference is the yellow ball has some velocity in the x. And that causes him, instead of landing directly beneath where he was dropped from, it has him land a certain number of centimeters, meters, etc. from that launch point. So, some people call projectile motion free fall, meaning you're falling purely under the influence of gravity. We know the acceleration due to gravity, etc., with horizontal motion, or a horizontal component. And that's not bad. The yellow ball is falling purely as if I dropped him straight down, at least from the y perspective. But I also give him a kick in the x direction. With that knowledge, working problems with projectile motion actually is not too bad, because I can work with things in the y direction exactly as if I was just tracking the red ball, which means it's no different than drop a ball straight down. The velocity in the y initially was 0 meters per second. Acceleration was acceleration due to gravity, negative 9.81 meters per second squared. Anything I want to solve for, final velocity at the bottom, time it takes to get to the bottom, all of that, I never even have to look at the fact that this guy was launched horizontally. Never has to enter into my problem solving. If all I want to know is how long does it take him to go from the top of the cliff or top of the table to the ground or the canyon floor, I can just look at the y direction. No different than just dropping something out of a window. Now this information right here, this little pocket of information, is generally not given to you necessarily on a test. It's expected you know it. So remember, when you're dealing with projectiles, this information is always in your pocket, whether or not they specify it. Now, in terms of projectiles and projectile motion, your basic kinematics formulas, ULAS, the same ones we worked with in previous chapters, guess what? It's the same ones you use now. Don't look in the book. Don't look in the book at all the derived formulas. So you see in the book a bunch of formulas that they derive specific for projectile motion. Go ahead and mentally scratch right through those. Don't even look at them. Go back on your formula sheet, the same kinematics formulas you used before, the ones you're going to use again. But what you're going to have to do is mentally modify some of them to use them specifically for the types of problems we're working with. When we're working with projectile motion, right there somewhere around, looking around page 96, make sure you can work with horizontally launched projectiles, such as, oops, not launched, it's launched. That's anything where all the velocity starts off in the x direction. That's going to be a car going off a cliff, a ball rolling off a table. That can also be a person throwing a dart straight horizontally, or a pitcher throwing a baseball straight horizontally. You should also be able to work with projectiles launched at an angle. That's a football kicked up into the air, a cannonball launched into the air, something along those lines, where I have a launch velocity that has both an x and a y piece. When I'm dealing with those projectiles launched at an angle, that initial launch velocity, when you're working in problems, the x component of that velocity is used. And that'd be vi cosine theta. There's my angle. That's used for anything where I'm looking at the horizontal motion of the projectile. The vertical velocity, or vi sine theta, is going to be used anytime I'm working with the vertical aspect of the velocity. Now, with both horizontal and projectiles launched at an angle, this value is constant. Acceleration is 0. This is accelerated, and we know the acceleration. It's acceleration due to gravity. Meters per second squared. There we go. So now, the video I also posted today works an example of both a horizontally launched projectile and a projectile launched at an angle. So I'm not going to go into detail with it in this video. But remember, when I have a horizontally launched projectile, the two things you're most likely going to be asked to solve for: how far horizontally does the ball travel, the car travel, the dart travel, the baseball travel, whatever it might be, and what was the velocity of the launch. For projectiles launched at an angle, the three things you will, and notice I'm kind of yelling will, be asked to solve for tomorrow. Again, how far does it travel horizontally? But also, how long is it in the air? And how high, ultimately, will this object travel? So for the horizontally launched projectile, what's delta x? You should be able to solve for. And what's v sub x? Your projectile motion lab, you solve for both of those in two different experiments. Projectile launched at an angle, how far, how long, and how high. So if you're a little shaky on those skills, again, I posted another video today that solves one of these, and also a non-perpendicular vector. There are also videos in previous days that solves for both of these types of problems. So feel free to go back and look at those. And that effectively is where the material for this particular chapter we're going to end. Material in this chapter, go ahead if you want to, whoops, there we have it, ends on page 99. End. The last section, which was relative motion, we're not doing. So not doing last section. So don't waste your time going over that material. It won't be on the test. Any questions or comments you have, you can email me today. I'll get back to you. You can stop in before school tomorrow as well. I'll be there as I always am, long before the sun seems to rise. So, good luck, and we'll see how things go.